or parameters is not nice. You want to have some clues about how to actually compute things in more detail. But this way, we first have to have good clues how to get quantum field theories out of this interpretation of quantum mechanics. And there's still a long way to go. So thank you very much for the invitation to come here to give lectures, and I can inspire some people to continue thinking.
Some questions? Yeah. Please come closer.
Yeah, some things you never mentioned, which is, one is uncertainty principle. And another thing is the density of particles. When you scatter there, to calculate real to experimental answer, you know that particles are indistinguishable from each other. Whereas how you put there in your information is that you have to sum up amplitudes and not that you cannot follow particles individually. So.
The uncertainty principle is precisely because you're working with observables that do not commute. Quite generally, X and P do not commute, but whenever you have two observables that do not commute, you have an uncertainty principle. That's a basic rule of quantum mechanics. And of course, in the B-balls, all the definition operators which commute. So there's no uncertainty at the level of the B-balls. So becomes, if you work with, let's say, quote unquote, the wrong states, a particle doesn't have position, doesn't have momentum, it is composed of B-balls. How to identify those B-balls is a big problem, and for neutrinos, I think I succeeded in doing that, but that's only a very small subset of all particles I really want to do it, so the rest is still quite a mystery. But once you have B-balls, you have all the commutators vanish, and so there's no uncertainty. And what's the second question?
About identical particles.
Identical.
How you distinguish, how you identify
fermions, when I described fermionization, the second quantization.
This you put anti-commutation.
The second quantization, I put the anti-commutator there, and so they are indistinguishable.
For bosons?
Bosons are a bit harder because the number of bosons is indefinite, and that at every spot you can have as many bosons as you want. And I think we should be able to do second quantization of bosons as well, but then there's more divergence in the whole situation, because we can have an integer that is an unspecified large number of bosons at the same spot. And I think what you really have to do is go to harmonic oscillators instead. And harmonic oscillators can be in quantum states or positive energy. Harmonic oscillators are very interesting. I haven't discussed them yet, but they are very interesting also to handle using the same philosophy. But so a bosonic particle is most aptly described by a bosonic field. And a bosonic field is basically a set of harmonic oscillators. So you have to understand the harmonic oscillator. That's a separate chapter.
So for your fermions are easier in a sense.
Sorry?
For your fermions are easier.
Fermions are easier. They are more
Because you put it here. It's already something quantum already when you put anti-commutators, right?
Yes, yes. So
in a sense, so it's not truly
But
classical.
the thing in bosons, in principle, not more difficult, but you have to worry about the indefinite number of bosons at a given spot. So we have to try to avoid that and replace them by harmonic oscillators instead, where we know essentially what it means to have the eigenstates of the harmonic oscillator.
Stability of the atom, so it's the same thing like in quantum mechanics normally. Why electron is not falling on the atom? Sort of.
Why electrons are not spoiling?
Why are not falling on the atom? It's uncertainty principle, sort of like that. So it remains. Why electron is stable?
Because you are not describing as being. So if you did, you would find that the logic is very different. In terms of B-balls, you saw the neutrinos as very special case. I couldn't make them interact yet, not in the first place. So it will be hard work to understand the atom in terms of B-balls rather than in terms of the standard description of the hydrogen atom.
Before the next question, will the important announcement for after? Okay. Okay.
Would would like to ask if there is such a scheme with the ontological vehicles, let's say, and this classical approximate vehicles in the sense of large entity. Is this still valid as a picture in the case of information loss, if we do information loss?
Oh, I have not discussed information loss, I'm sorry. I should have had more time. There is, what I've discussed so far is a theory where the evolution can go forward as easily as backward in time. The big question is, once you have deterministic theory, why should that be necessary? And in fact, I believe it's not necessary. The current theory, where evolution forward in time, can no longer be traced back to the past. For a simple reason that two different states might evolve in the same state in the future. That's called information loss. At first sight, it seems that would be totally in disagreement with what I said here. So there should be no information loss in the deterministic system, otherwise you can't do this quantum trick. But that's jumping to conclusions a bit fast. In reality, I can perfectly well accommodate for information loss, but things become a hell of a lot more complicated. And, but there's one enormously big advantage of information loss, and that is that I can add a fifth thing here, which is the error of time. The error of time is very mysterious. In ordinary classical mechanics, quantum mechanics and the like, why does nature evolve one direction of time into the opposite? The answer could be information loss. Now, you would say information loss would violate time reversal symmetry, that would violate PCT symmetry. No. If I apply the tricks, which I haven't explained to you unfortunately, of quantum mechanics, in the case of information loss, you discover the underlying quantum mechanics of the PCT is variant again. So there will be a perfect symmetry at the quantum level, but now at the behavioral level, there will be an enormous difference between going forward in time and going backwards in time. So there will be a natural error of time. So that's what I like about the idea of having information loss. You solve the fifth thing here, which is the error of time. But now time has a definite error in the micro theory, which it did not have at the level of the microstates, of the templates, and also not at this. Well, classically, yes, of course, classically there's an error of time, but here there is not. And this is only a problem. Now I say that's a deficiency of our way of using quantum mechanics as a tool, that tool hides the fact that here things might be asymmetric in the time reversal, but it resurfaces at this level. So there's something very interesting about time reversal, which I should have added then.
Now, another question at the back? No, maybe so.
Okay. In this picture, what is the meaning of, what is the interpretation of renormalization? There is another, you can discuss this point.
Correct. Of course, the standard model is a quantum field theory, and that quantum field theory has to be renormalized. And I think actually renormalization is very important. It just shows to you that if you formulate something at a Planck scale, say, imagine I managed to reproduce a quantum field theory at a Planck scale. Now, I have to understand how that generates a standard model. I have to run from the Planck scale dimensions to the standard model dimensions, some 50 orders of magnitude or so, and that is, of course, using the renormalization tool. So that's where renormalization goes in. By the time I reach the standard model scale, only the marginal or the significant couplings survive. All the insignificant ones, which are higher order, higher scale dimension or couplings, will have disappeared. They don't survive the journey from the Planck scale to the standard model scale. So that automatically turns the standard model into some renormalizable theory. As long as couplings are small, they should behave like renormalizable couplings. And if they are strong, well, you have a strong potential theory, it's more complicated. But so if there is a natural explanation to why standard model is renormalizable. If I manage to do my trick at the Planck scale, the rest will follow and will be renormalizable automatically. But the difficulty is to get started at the Planck scale.
And about locality, I imagine that in this picture with brackets, with this discretization, there is something like in lattice to CD with a Wilson operator, something non-local. And on the other hand, there are some theorems about problems in chirality, in the reproduction of chirality in lattice to CD. So how?
Okay. Well, lattice usually has a lattice, of course, at the of the scale of the standard model scale. So, and that is considered usually to be an approximation of the theory with its own shortcomings as being an approximation. So, I'm now considering those lattices of Planckian dimensions, where I think these problems have to be solved together, not one by one in succession. So once you generate a lattice theory, you generate something that looks, well, I don't know whether QCD makes any sense at the Planck scale. It will be a very weakly interacting theory, so that some of the difficulties that we encounter in real lattice theories never show up. Of course, the usual difficulties with chirality of the phenomens means that things are not going to be easy to do. And you just mentioned one of the many problems that one will encounter when you try to actually implement the program at full depth. Then sooner or later, yes, one will see that perhaps also at the Planck scale there are chiral phenomens. How many phenomens it will be and what the standard model will look like at that scale, nobody knows yet. But of course, we want to understand how the anomalies of the kind of nature, how nature manages those anomalies, and those will be undoubtedly important questions at the level. But I actually doubt whether a simple lattice will come out or something much more complicated that only looks like a lattice in some vague sense. And I'm sure nature has found a solution to how to deal with the anomalies.
Yes, it seems to me that if you think it to the consequence, the last consequence of your feature of your theory, then there is only one beagle. It is the beagle of the universe, and it is not reproducible. Nothing is reproducible because you can't go back in time. So, because evolution is deterministic in your theory, when you say that, then wouldn't be any, not even the need to introduce 2 or 3 or 4 beagles, because the universe is just one of them, but you would never know what it is.
Well, that's probably a little bit too agnostic. I think what makes physics work is a notion of locality and causality and all the other symmetry properties. For instance, locality tells us that if you know laws of nature just at this point, we can apply translation symmetry to find how nature behaves at all the other points. So translation symmetry is a very important symmetry. Without translation, you would have locality and you would understand. You would have been in the situation as you just sketched, that you can just, well, take anything and decide that the laws of nature are being invented everywhere that things take place. That's not a very nice theory of nature, you would know nothing. So our lies and philosophy is based on the assumption that nature is reproducible and things happening here will repeat, happening elsewhere, happening elsewhere. And that's of course something that you want to put in. If not, then we're not doing physics. So I think that this is one element that we definitely have to use, element of locality, and element that beagles are reproducible. So a beagle here looks like a beagle there, and laws of nature could be somehow compressed into a very neat set of laws that takes place very locally, and the same laws will take place somewhere else. And if that would not be assumed, you will be nowhere. So I think yes, you have to make such assumptions in order to make progress in physics at all. I don't know whether that answers the question, but at least I know.
There will be another question from the panel,
I have not understood why it is important in your definition of beagle that These operators commute also at different times. Can you explain that?
Well, if they would not commute at different times, then you would have just generic quantum theory. And in a deterministic system, I don't know what that means. In a deterministic system, like the planetary system, all positions of planets commute at all times. So if you want the deterministic theory, the beam should commute at all times. If you give that up, you get non-commuting things, and then you're back at ordinary quantum mechanics, and then we have the standard model as it is with all its freely adjustable parameters. And we want to find something better, which is something really predictable. That is why I want, well, the bet is that nature is deterministic at the Planck scale, the consequence of that is things will commute at all times. So, you don't have to take that, of course, you can think of a different theory, and then think of another.
But the evolution
The evolution of operators is anyway deterministic also in some kinds. Probability comes after.
In ordinary theories of nature, such as a standard model or any other quantum field theory, it is like the way you say that operators now are not commute operators in the future. If you make a change in operator here, and very probably change the operators in the future. So indeed, yes, things do not commute at different times. Now, the thing that I'm investigating is the possibility that things do commute. So you say it doesn't, well, that's not a theory. The B also saying they commute in time, and the idea that you can make a complete base of states and build out vehicles. That's the assumption. The assumption may be wrong, and then you have the problem that you mentioned. Things not commute at later times.
Sorry.
Camillo, as I check the microphone.
Just to make sure that it's a very important feature of your proposal that the time evolution preserves the vivo state basis, right?
Yes.
So it doesn't mean that it's unavoidable, the discreteness of time evolution, or don't you think that's an unavoidable feature? Because otherwise the continuous thing would be difficult to think that how can preserve the state.
Time evolution doesn't have to be discrete. In fact, what you could do is even have theory in discrete time, like a clock on a clock wheel. You can always say the thing hops from this state to that, but it goes through millions of intermediate states. And you can add those intermediate states to physics. The question now is simply what's the most economical way to describe things. And that could be ambiguous. That question might have a very unique answer. We just want to be efficient as physicists. We don't want to use more than necessary. So I started discrete time with the idea that that's the minimal I have to demand. But maybe we can fill in the epochs between two discrete time steps, and then we get continuous time. Maybe nature doesn't care what you do there, that we can fill in those intermediate time to make our lives more difficult. We want to find the easiest possible description. And in many easy models, as I described before the page, you have discrete time steps. That's the easiest way to describe how things work. But it could be ambiguous. It could be that is not quite a well-defined question whether time is discrete or continuous. It hops. Things hop from one time to the next. Whether there's something in between, well, time goes on. We have no time to stand still at intermediate states. Maybe they exist, maybe they do not exist.
Okay, I would like to wrap up the fourth series of the Majorana lectures, whose success is given by the fact that it's very difficult to conclude them because we are still working. But I would like to thank, of course, the speaker. Thank him several times. And we also have to apologize because we subjected him to anything from selfies with this was the university to really lots of questions, and so we thank and apologize for the success of your lectures. There are other people to thank. First of all, our hosts of the Giampiero, that is the coordinator of the Gruppo Quarto, the theory group, and the director of the section, Giovanni Larana, that is there. So several people did a lot of work to make things working, and listing them. Luigi Coraggio was the microphone things. Angela Gargano, Nunzio, Angela even took care of the coffee and the sweets. Franco Pezzella, Lello Marotta is our Novello Sorrentino making things. And I would also to thank somebody who is not here, but is Giancarlo Greca. He was very efficient in all the administration up there. And finally, I would like to thank, of course, everybody that came, and especially the people that came from other places in the region and outside of the region, and even from farther away. And so I think that we can finish this fourth successful series of the Majorana lectures.